Picture this: a pulse of energy so intense it can outshine an entire galaxy, but so fleeting it vanishes before you can blink. These are fast radio bursts, some of the most enigmatic signals ever detected from the depths of space. For years, they've defied explanation, appearing without warning, racing across the cosmos, and leaving scientists scrambling for answers. What could possibly produce such a staggering burst of power in just milliseconds? The more we learn, the stranger the mystery becomes. Some of these signals repeat, while others vanish without a trace. Some originate from billions of light years away, carrying secrets from the far reaches of the universe. And the theories, they're as wild as they are fascinating: colliding neutron stars, evaporating black holes, or even, just maybe, the fingerprints of an advanced extraterrestrial civilization. But here's what's truly mind-blowing. Fast radio bursts aren't just cosmic oddities. They might hold the key to understanding some of the universe's biggest questions. By studying these bursts, astronomers have mapped invisible matter between galaxies, tested the fabric of space-time itself, and even uncovered clues about the origins of the cosmos. Each new detection is like a message in a bottle, washed ashore from the depths of space, waiting to be decoded. And with every mystery solved, a dozen more take its place. So today, we're diving deep into 30 of the most baffling radio bursts ever recorded, signals that challenge everything we think we know about the universe. We'll explore where they come from, what they might mean, and why scientists are so obsessed with cracking their code. From the first accidental discovery to the latest cutting-edge research, this is a journey to the edge of our cosmic understanding. And who knows, by the end, you might just look up at the night sky a little differently, wondering what other secrets are hidden in the silence between the stars. Let's begin. The story of fast radio bursts begins not with a eureka, a moment under the stars, but in the quiet hum of a data archive. In 2007, astronomer Duncan Lorimer was sifting through old observations from the Parkes radio telescope in Australia when he stumbled upon something extraordinary: a single spike of radio waves so powerful it dwarfed the background noise of the cosmos. Lasting just 5 milliseconds, this burst had traveled billions of years across the universe before reaching Earth, carrying the energy of 500 million suns. At first, some dismissed it as a glitch, but when similar signals started appearing in other telescope data, the scientific community had to confront a startling truth. We were detecting cosmic fireworks unlike anything seen before. What made these bursts so baffling wasn't just their staggering power. It was their sheer unpredictability. Unlike pulsars, which tick with the regularity of a cosmic clock, these bursts appeared without warning, vanishing before astronomers could even swing their telescopes toward the source. The first detected burst, now known as the Lorimer burst, seemed like a one-off event, a cosmic lightning strike with no explanation. But as more were discovered, patterns began to emerge. Some bursts repeated, firing off multiple signals from the same patch of sky. Others carried a strange fingerprint, a telltale distortion caused by passing through vast clouds of intergalactic plasma, revealing just how far they'd traveled. The implications were staggering. If these bursts were coming from billions of light years away, their sources had to be unimaginably powerful. Neutron stars, the collapsed cores of dead suns, became prime suspects, especially when one repeating burst was traced to a highly magnetized neutron star called a magnetar. But not all bursts fit this explanation. Some were too energetic, too isolated, or too strangely structured. Theorists began floating wilder ideas: cosmic strings snapping like rubber bands, black holes evaporating into showers of particles, or even whisper it alien megastructures beaming signals across the void. What's fascinating is how this mystery has transformed astronomy. Fast radio bursts aren't just cosmic curiosities, they're tools. By measuring how these signals twist and scatter as they traverse the universe, scientists have mapped the invisible web of matter between galaxies, weighed the missing atoms of the cosmos, and even tested Einstein's theory of relativity. Every new burst is like a flare in the darkness, illuminating the structure of space itself. And with each discovery, the story grows richer. From that first archival anomaly to the hundreds detected since, one thing is clear: the universe is speaking in bursts. And we're only just beginning to listen. Fast radio bursts are cosmic lightning strikes, blindingly bright, impossibly brief, and packed with mysteries. Lasting mere milliseconds, these bursts unleash more energy than our sun produces in days, sometimes even years. But what makes them truly extraordinary isn't just their power, it's how they reveal themselves. Each burst spans a range of frequencies, from the low hum of radio waves to the higher pitches of microwaves, creating a distinctive sweep in the data astronomers call a dispersion measure. This sweep isn't just static, it's a cosmic roadmap. The longer the burst's waves take to arrive, the more intergalactic material they've traveled through, letting scientists calculate distances spanning billions of light years. It's like hearing an echo in a cavern and knowing, just by its delay, how vast the space around you must be. Then there's the puzzle of repetition. Some bursts fire once and vanish forever, cosmic one-hit wonders leaving astronomers scrambling for clues. Others, like the now famous FRB 1211-2, repeat with erratic but undeniable regularity, flickering on and off like a malfunctioning cosmic beacon. This split between one-offs and repeaters hints at two entirely different origins. Repeaters tend to cluster in magnetically violent environments, often near the corpses of massive stars or swirling debris from galactic collisions. Their sporadic but recurring nature suggests a source that survives the outburst, like a magnetar, a neutron star with a magnetic field so intense it could strip the data from a credit card halfway across the Milky Way. Single bursts, though, they're the true wild cards. Theories range from cataclysmic finales, neutron stars collapsing into black holes, or the explosive mergers of unimaginably dense objects, to more exotic possibilities, like the theoretical blitzars, where a spinning neutron star's own centrifugal force tears it apart in a single, brilliant flash. Even stranger, some bursts exhibit substructure, tiny pulses within pulses, as if the source is convulsing in ways we can't yet explain. Yet for all their differences, every fast radio burst shares one tantalizing trait: they're messengers. As these signals race across the universe, they pass through the sparse gas between galaxies, subtly altering their signature. By decoding these changes, astronomers have mapped the universe's hidden scaffolding, the elusive matter that makes up the cosmic web. It's as if each burst carries a snapshot of the spaces it's traveled through, revealing voids and filaments we'd never see otherwise. The more we learn, the clearer it becomes these bursts aren't just cosmic anomalies. They're keys to understanding the universe's structure, its history, and perhaps even the fate of matter itself. Every detection is a clue, and every unanswered question. Well, that's just another reason to keep listening. Among the cosmic chaos of fast radio bursts, the repeaters stand apart, not as cosmic fireworks that fizzle into nothing, but as persistent enigmas that refuse to stay silent. Take FRB 1211-2, the first known repeater discovered in 2016. Unlike one-off bursts that scream into the void and vanish, this one flickered back to life weeks after its first detection, then again and again, like a distant lighthouse with no predictable rhythm. Its very existence shattered early assumptions that all bursts were tied to catastrophic, one-time events like colliding neutron stars or dying black holes. Here was something different, a source that endured, capable of unleashing multiple bursts without destroying itself. The implications were profound. If repeaters aren't self-destructing, their origins must lie in objects that can survive these violent outbursts. Enter Magnetars, neutron stars with magnetic fields so intense they could warp atoms into needle-thin shapes from thousands of light-years away. When these cosmic powerhouses experience starquakes, sudden fractures in their ultra-dense crusts, they can unleash torrents of energy, including fast radio bursts. Observations in 2020 seem to confirm this when a magnetar in our own galaxy, SGR 1935+2154, erupted with a burst strikingly similar to those from distant repeaters. Finally, a smoking gun, or so it seemed, but the plot thickens. Not all repeating bursts match the magnetar profile. Some, like FRB 1810-156, fire off with bizarre symmetry, clusters of bursts separated by eerily consistent pauses, as if governed by some unseen cosmic metronome. Others exhibit sad trombone effects, their signals sliding down in frequency like a cosmic glissando, hinting at plasma-filled environments or bizarre magnetic interactions. And then there's the sheer variety. Some repeaters spit out hundreds of bursts in a frenzied weekend, while others, like FRB 1800-316, take years between encores. What's truly baffling is the why behind the repetition. If magnetars are the culprits, why don't all of them produce bursts? And why do some repeaters seem to activate only in sporadic, unpredictable fits? One theory suggests these bursts might be powered by asteroid-sized chunks of debris falling onto magnetars, creating violent plasma shocks. Another posits cosmic short circuits in the star's magnetic field, like a frayed power line sporadically sparking. And then there's the wild card. Could some repeaters be signs of advanced civilizations using directed energy to propel spacecraft, as some have speculated? While that idea remains firmly in the realm of hypothesis, it underscores just how open this mystery still is. What makes repeaters so invaluable to astronomers isn't just their persistence, it's their predictability. Unlike one-off bursts that vanish before follow-up observations can begin, repeaters give scientists a second chance, a third, even 100th. Each new burst from the same source is another piece of the puzzle, revealing subtle changes in polarization, frequency, or timing that might unlock their origins. Already, they've led us to cosmic environments unlike anything in our galaxy, dense nebulas choked with magnetic turbulence, or the turbulent neighborhoods of supermassive black holes. Yet for every answer, repeaters pose a dozen new questions. Why do some seem to turn off for years before reactivating? What explains the bursts within bursts, those microsecond subpulses that hint at unseen structures in the emission process? And could there be a continuum between repeaters and one-offs, with some sources simply operating on timescales too long for us to yet detect? The more we learn, the clearer it becomes. These aren't just cosmic anomalies. They're windows into the universe's most extreme physics, and perhaps the keys to understanding how matter behaves under conditions we can scarcely replicate on Earth. One thing's certain: when a repeater flares up again, the world's telescopes swing into action, because in those fleeting milliseconds, the universe is handing us a clue. And this time, we might just be ready to listen. If repeaters are the cosmic lighthouses flickering in the distance, one-off fast radio bursts are the universe's fireworks, spectacular, unpredictable, and gone in an instant. These singular bursts make up the majority of detected FRBs, yet their fleeting nature makes them infinitely harder to study. unlike their repeating cousins, one-offs leave no second chances. Miss that millisecond window and the opportunity vanishes forever, like a cosmic magic trick with no encore. What could possibly produce such a violent, one-time burst of energy? The leading theories read like a list of the universe's most extreme events. Imagine two neutron stars, city-sized remnants of dead suns, each so dense a teaspoon of their material would weigh 1 billion tons, spiraling toward each other in a deadly dance. When they finally collide, the impact unleashes a shockwave of energy capable of bending spacetime itself, potentially birthing a black hole in the process. That catastrophic merger could blast out a fast radio burst as its final signature, a farewell note etched into the fabric of the cosmos. But neutron-star collisions might not be the only explanation. Some theorists point to blitzars, a hypothetical phenomenon where a spinning neutron star's own rotation prevents it from collapsing into a black hole until suddenly it can't resist gravity's pull anymore. In its death throes, the star's magnetic field lines snap like rubber bands, releasing a torrent of energy as it vanishes into a black hole. Others speculate about cosmic strings' theoretical cracks in spacetime left over from the Big Bang, slipping and releasing pent-up energy like a snapped guitar string ringing across the universe. Then there's the black hole evaporation theory, inspired by Stephen Hawking's groundbreaking work. If a tiny primordial black hole, one formed in the chaos of the early universe, finally evaporates after billions of years, its death could produce a burst of radiation detectable as an FRB. It's a haunting thought. These bursts might be the last gasps of black holes that have silently wandered the cosmos since the dawn of time. The challenge with one-offs isn't just theorizing their origins, it's catching them in the act. Unlike repeaters, which announce their locations with multiple bursts, one-offs require astronomical luck to pin down. Telescopes like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, have revolutionized the hunt by scanning huge swaths of sky continuously, turning what was once a game of chance into a systematic search. When a one-off bursts onto the scene, astronomers have mere seconds to alert other observatories worldwide, racing to capture any lingering afterglow in X-rays, visible light, or other wavelengths before it fades forever. This urgency has led to some of the field's most dramatic moments. In 2019, a one-off dubbed FRB 190523 made history when scientists traced it back to a galaxy 4 billion light-years away, only the third one-off ever localized. The host galaxy surprised researchers, a relatively ordinary spiral, not the turbulent star-forming regions often associated with magnetars. This discovery hinted that one-offs might arise from entirely different environments than their repeating counterparts, adding yet another layer to the mystery. Perhaps the most tantalizing aspect of one-offs is what they might be hiding. Could some of these single bursts actually be repeaters with cycles too long for us to detect? Or are we seeing multiple phenomena lumped together under one label with colliding stars, dying black holes, and who knows what else all contributing to the mix? Every unanswered question makes these bursts more than just cosmic oddities. They're invitations to rethink our understanding of the universe's most violent phenomena. While repeaters give us multiple shots at decoding their secrets, one-offs are like rare, shattered artifacts. Each fragment tells a story, but we may never find all the pieces. And that's what makes them irresistible. They remind us that for all our telescopes and supercomputers, the universe still holds cards it hasn't shown us yet. So when the next one-off flares across the sky, somewhere a team of astronomers will be holding their breath, hoping this time, just maybe, the universe will let its guard down for a millisecond long enough for us to catch a glimpse behind the curtain. The journey of a fast radio burst is nothing short of epic, a pulse of energy racing across the unfathomable voids between galaxies, enduring billions of years just to reach us. These signals aren't homegrown mysteries of the Milky Way. They're interstellar travelers carrying secrets from galaxies so distant their light predates Earth itself. What makes this even more astonishing is how they reveal their origins. Each burst's dispersion measure, that telltale sweep of frequencies, acts like a cosmic odometer, tallying the vast stretches of plasma it's traversed. The higher the measure, the longer the journey, with some bursts clocking in at values that place their origins in galaxies billions of light years away. But here's where it gets truly fascinating. The neighborhoods these bursts call home are as varied as the universe itself. Take FRB 1211-2, the first repeater ever localized. It hails from a tiny, unassuming dwarf galaxy, a cosmic backwater with barely a fraction of the Milky Way stars. At first glance, this seems improbable. How could such a faint galaxy produce bursts energetic enough to outshine entire galaxies? Then there's FRB 190523, which traces back to a spiral galaxy not unlike our own, while others have been linked to regions near supermassive black holes where gravitational forces warp spacetime itself. This dizzying diversity suggests fast radio bursts aren't picky about their real estate. They emerge from bustling galactic cores, quiet stellar nurseries, and everything in between. Why such a range? One possibility is that the mechanisms behind these bursts are universal, capable of igniting under wildly different conditions. Magnetars, for instance, might lurk in both dwarf galaxies and massive spirals, their outbursts indifferent to their surroundings. Alternatively, the environments themselves could shape the bursts in ways we're only beginning to understand. A magnetar near a black hole might behave differently than one floating in isolation, its magnetic field twisted by tidal forces or fueled by nearby debris. Even the intergalactic medium plays a role. Bursts passing through dense galactic halos or filamentary cosmic webs arrive with subtle distortions, like light filtering through stained glass. Then there's the tantalizing clue of star formation. Some host galaxies, like the one housing FRB 1810-156, are veritable fireworks factories, churning out new stars at a frenetic pace. This hints that young, massive stars, those destined to collapse into neutron stars or magnetars, might be key players. Yet other bursts originate in galaxies where star formation fizzled out eons ago, forcing astronomers to reconsider the connection. Could there be multiple paths to creating these bursts, with some tied to stellar youth and others to ancient, dormant objects? What's undeniable is that fast radio bursts are cosmic egalitarians. They don't discriminate between galaxy types, sizes, or ages. This universality makes them invaluable probes, offering snapshots of environments we'd otherwise never glimpse. By studying their host galaxies, astronomers have stumbled upon unexpected patterns, like dwarf galaxies punching above their weight in burst production, or the curious absence of bursts from the most massive, metal-rich galaxies. Each discovery peels back another layer, revealing how these enigmatic signals are woven into the fabric of the universe itself. So the next time a fast radio burst flickers onto a telescope's readout, remember, it's more than a blip of energy. It's a postcard from a galaxy far, far away, stamped with the fingerprints of everything it's passed along the way. And with every new burst localized, we're one step closer to understanding why the universe chooses such wildly different corners to broadcast its most fleeting messages. When it comes to explaining fast radio bursts, scientists have a cosmic menu of possibilities, each theory more mind-bending than the last. At the top of the list, magnetars. Picture a neutron star, the collapsed core of a supernova. but crank its magnetic field up to 1,000 trillion times stronger than Earth's. These cosmic powerhouses operate like celestial Tesla coils, capable of unleashing starquakes, violent ruptures in their crust that send shockwaves through their magnetospheres. When these quakes occur, they can whip magnetic field lines into a frenzy, snapping them like overstretched rubber bands and releasing millisecond flares that outshine entire galaxies. The smoking gun came in 2020, when a magnetar just 30,000 light-years away in our own galaxy let loose a burst eerily similar to distant FRBs. Finally, astronomers had a nearby lab to study the phenomenon, yet magnetars alone can't explain the full spectrum of bursts. Some FRBs pack too much energy or appear in environments where magnetars seem unlikely. That's when neutron star mergers enter the scene. Imagine two ultra-dense stellar corpses locked in a death spiral, their gravitational dance warping spacetime until, bang, they collide. The resulting shockwaves could generate a one-off burst, a final cosmic scream before the stars vanish into a black hole. Supporting this idea, some FRBs arrive with a subtle afterglow in other wavelengths, hinting at the kind of debris you'd expect from a catastrophic collision. But the universe loves variety, and so do FRB theories. Some bursts might originate from the poles of supermassive black holes, where magnetic fields funnel matter into jets traveling near light speed. These jets could act like interstellar particle accelerators, producing bursts when particularly energetic clumps collide with surrounding gas. Then there's the wild card, primordial black holes, tiny, ancient relics from the Big Bang evaporating in a blaze of Hawking radiation. Even cosmic strings, hypothetical defects in spacetime, get a mention. If they exist, their vibrations might ripple outward as FRBs. And yes, the elephant in the room, alien technology. While most astronomers consider this a last resort explanation, the sheer power and structure of some bursts have prompted speculation. Could advanced civilizations be using focused energy beams to propel light sails across galaxies, with FRBs as accidental byproducts? It's a tantalizing thought, but one lacking concrete evidence. The real takeaway: the diversity of FRBs suggests we're not dealing with a single phenomenon, but a cosmic zoo of origins. Some bursts fit the magnetar mold perfectly, while others demand entirely new physics. This theoretical free-for-all isn't just academic, it's a reminder of how much we still don't know. Every new burst that defies categorization forces scientists to revisit their playbooks, tweaking models or inventing entirely new ones. The beauty lies in the chaos. FRBs refuse to be pigeonholed, and that's what makes them such powerful tools for discovery. Whether they are born from dying stars, colliding black holes, or something beyond our current imagination, one thing's certain: the universe has more tricks up its sleeve than we ever suspected. Magnetars might just be the universe's ultimate cosmic power plants. Stellar remnants so magnetically charged they make Earth's magnetic field look like a refrigerator magnet. These exotic objects form when a massive star collapses under its own gravity, compressing into a dense core barely 20 kilometers across, yet spinning hundreds of times per second with magnetic fields strong enough to distort atoms from thousands of light-years away. It's no wonder they've become the prime suspects behind repeating fast radio bursts. The case strengthened dramatically in 2020 when a magnetar named SGR 1935+2154, lurking right in our galactic backyard, erupted with a millisecond burst eerily similar to those from distant galaxies. For the first time, astronomers had front-row seats to a potential FRB in action, complete with the telltale energy spike and rapid fade. But here's the catch: magnetars are chaotic beasts, not precision instruments. Their bursts vary wildly in intensity, from faint crackles to planet-frying flares. Some, like the one observed in 2020, line up neatly with the energy profiles of known FRBs. Others, though, fall short. The most extreme fast radio bursts detected, like FRB 190523, which carried the energy of 500 million suns, push magnetar physics to its limits. Could a single starquake or magnetic reconnection really unleash that much power? Or are we missing something deeper in the magnetar playbook? Then there's the timing puzzle. Repeating FRBs often fire off in clusters, a flurry of bursts over days or weeks, followed by eerie silence. Magnetars exhibit similar sporadic activity, but their outbursts tend to be less predictable. Some go decades without a peep, while others, like SGR 1806-20, produce hundreds of flares in a single year. This inconsistency leaves gaps in the theory. If magnetars are the sole engines behind FRBs, why don't all magnetars produce them? And why do some bursts, like those from FRB 1211-2, repeat with near clockwork precision, while others seem to follow no discernible rhythm? One intriguing possibility is that magnetars need accomplices. Imagine a magnetar shrouded in a dense nebula of debris, leftover material from the supernova that birthed it. When asteroids or comets plunge into this environment, the resulting plasma shocks could amplify the star's magnetic outbursts, turning a standard flare into an FRB-scale event. Alternatively, interactions with a binary companion, a second neutron star, or even a black hole might twist the magnetar's magnetic fields into explosive configurations. These scenarios could explain why some bursts are so much more energetic than others, and why they emerge from such diverse galactic environments. Yet magnetars alone might not tell the whole story. While they're a compelling fit for many repeating FRBs, the universe has a habit of serving up surprises. Some bursts exhibit polarization patterns so extreme they suggest magnetic fields far stronger than even magnetars should possess. Others arrive with no trace of a host galaxy, as if launched from the voids between galaxies, a place where magnetars are unlikely to form. These outliers hint at a broader zoo of FRB sources, with magnetars as just one species in the cosmic menagerie. What makes magnetars so fascinating isn't just their potential link to FRBs, it's how they force us to rethink the boundaries of physics. Their magnetic fields are so intense they can literally break the rules of quantum electrodynamics, creating conditions impossible to replicate on Earth. Every burst they produce, whether it matches an FRB or not, is a laboratory for extreme science. And as telescopes grow more sensitive, we're catching these events in ever greater detail, peeling back the layers of their mysteries one outburst at a time. So while magnetars might not be the only players in the FRB drama, they've earned their spotlight. They're cosmic wildcards capable of both illuminating the universe's secrets and reminding us how much we still have to learn. And in that tension between what we know and what we've yet to discover lies the thrill of the hunt. Neutron-star collisions are among the most violent events in the universe, a cosmic demolition derby where two stellar corpses, each more massive than our sun but no wider than a city, spiral toward oblivion. When they finally meet, the impact unleashes energies that ripple spacetime itself, sending gravitational waves across the cosmos while lighting up the sky with gamma-ray bursts. But could these cataclysmic mergers also be the hidden engines behind some fast radio bursts? The math is tantalizing. A single neutron star collision can release more energy in seconds than our sun will emit in its entire lifetime, more than enough to power an FRB's blinding flash. The idea gained traction after the historic detection of GW 170817 in 2017, when gravitational wave observatories caught the tremors of two neutron stars colliding. Alongside the gravitational waves, telescopes spotted a gamma-ray burst and a lingering afterglow, proof that these mergers are cosmic fireworks factories. Yet no definitive FRB was detected, leaving a critical question unanswered. If these events can produce FRBs, why don't we see more of them? Part of the challenge is timing. Neutron star mergers are vanishingly rare, with perhaps just a handful occurring in a galaxy like ours every million years. Yet fast radio bursts seem to pepper the universe far more frequently, with some estimates suggesting thousands might occur across the sky every day. If every FRB required a neutron star collision, the cosmic death toll would defy what we know about stellar populations, unless, of course, we're missing something. One possibility is that not all mergers are created equal. Imagine a neutron star duo where one partner is highly magnetized, a magnetar in waiting. Their collision might not just produce gravitational waves and gamma rays, but also a magnetic maelstrom capable of launching an FRB. Alternatively, the debris from such a crash could form a short-lived hypermassive neutron star, its magnetic fields twisting into knots before the object collapses into a black hole, releasing a final, brilliant burst. The plot thickens when you consider the afterglow problem. Most localized FRBs show no trace of the lingering emissions typically seen after neutron star mergers, no X-ray echoes or infrared flares. This silence suggests that if mergers are involved, they are either happening in environments that suppress afterglows, or the FRB mechanism is somehow divorced from the merger's other byproducts. Then there's the gravitational wave dilemma. While observatories like LIGO and Virgo grow more sensitive, they've yet to detect space-time ripples coinciding with an FRB. If neutron star collisions were a dominant source, these overlaps should be more common. Unless, as some theorists propose, FRBs are beamed focused into narrow jets that only Earth-bound observers directly in the line of fire would detect. In that case, the gravitational waves from the merger might be too faint to register unless the event happened relatively nearby. What's fascinating is how this debate mirrors astronomy's broader struggle to explain cosmic extremes. Neutron star collisions check many boxes for FRB production: raw energy, magnetic chaos, and the capacity for repetition if multiple fragments survive the crash. But the universe rarely follows tidy scripts. Perhaps these mergers explain only a subset of bursts, leaving room for magnetars, evaporating black holes, and other exotic phenomena to fill the gaps. Every unanswered question is a reminder of how much we're still learning about the universe's most violent symphonies. Neutron star collisions may not be the sole architects of FRBs, but they're a compelling piece of the puzzle, one that challenges us to keep listening, watching, and waiting for the next cosmic encore. Black holes, those bottomless pits of gravity where even light can't escape, might seem like unlikely suspects in the fast radio burst mystery. But in the extreme physics of the cosmos, the unimaginable becomes routine. Picture a star wandering too close to a supermassive black hole, its immense tidal forces stretching the star like taffy in a process called a tidal disruption event. As the star shreds, its material swirls into a superheated disk around the black hole, sparking jets of particles blasting outward at nearly the speed of light. These jets, funneled by the black hole's twisted magnetic fields, could act like cosmic particle accelerators, generating shockwaves violent enough to produce FRBs as they collide with surrounding gas. Evidence is mounting that some bursts emerge from the neighborhoods of supermassive black holes. Take FRB 190608, traced to a galaxy with an active galactic nucleus, a voracious black hole devouring surrounding matter. Others, like FRB 150435, originate near regions where black hole jets punch through intergalactic space, their polarized signals hinting at magnetic environments only a black hole could create. These associations aren't coincidental. the energy scales match. A single tidal disruption event can unleash 1,000,000 times more energy than our Sun will emit in its lifetime, easily fueling an FRB's brief but staggering brilliance. Yet mysteries linger. If black holes are FRB factories, why don't we detect bursts from every active galaxy? And how do some FRBs, like those repeating from dwarf galaxies, fit into this picture when their hosts lack supermassive black holes altogether? The answer might lie in black hole diversity. Intermediate mass black holes, elusive objects weighing thousands of suns, could generate bursts in smaller galaxies, while hidden black holes shrouded in thick dust clouds might produce FRBs we've mistakenly attributed to other sources. Then there's the wild card, primordial black holes. These hypothetical relics from the Big Bang, some no heavier than a mountain, could evaporate in a flash of Hawking radiation, potentially leaving behind an FRB as their final cosmic signature. While speculative, the idea underscores how black holes of all sizes might be whispering to us through these bursts. What's clear is that if black holes are involved, FRBs aren't just flashes in the dark, they're signposts pointing to the universe's most chaotic environments. Every burst near a black hole's domain offers a chance to study how matter behaves under gravity's most extreme dictatorship. And in those fleeting signals, we might just find clues to questions we haven't even thought to ask yet. Fast radio bursts don't just defy expectations, they smash through them, leaving astronomers scrambling for explanations that stretch beyond textbook astrophysics. Enter cosmic strings, hypothetical cracks in the fabric of space-time left over from the universe's fiery birth. Picture these defects as cosmic fault lines, thinner than an atom but stretching across galaxies, vibrating like snapped guitar strings. If one were to wiggle or snap, the energy released could theoretically ripple outward as an FRB, a fleeting echo of the universe's infancy. It's a wild idea, but one that underscores how little we truly understand about spacetime's underlying structure. Then there's the eerie possibility of primordial black holes, tiny, ancient relics forged in the chaos of the Big Bang. Unlike their stellar-born cousins, these black holes could be as light as a mountain or as heavy as a star, lurking unseen for billions of years. According to Stephen Hawking's groundbreaking work, such objects would slowly evaporate, their final moments marked by a burst of radiation. Could some FRBs be the death cries of these primordial beasts? The math is tantalizing. A black hole weighing 1 billion tons would vanish in a flash of energy comparable to an FRB's brilliance, leaving no trace behind. What makes these theories so compelling isn't just their audacity, it's their sheer testability. Cosmic strings, if they exist, would warp the space around them, bending light in ways astronomers could potentially detect. Primordial black holes might reveal themselves through subtle gravitational lensing effects or the unique signatures of their evaporation. Every new FRB detection becomes a potential clue, a chance to rule out or confirm physics that currently lives only on chalkboards and in supercomputer simulations. Yet for all their intrigue, these exotic explanations come with caveats. Cosmic strings remain purely theoretical, their existence inferred from elegant equations rather than hard evidence. Primordial black holes, while plausible, have eluded every search so far. And then there's the sheer diversity of FRBs themselves. Some bursts repeat, others vanish forever. Some are highly polarized, others scatter like radio static. No single exotic model can explain them all, suggesting the truth might be even stranger. A cosmic menagerie of phenomena, some familiar, others beyond our wildest imagination. That's the real magic of FRBs. They're not just cosmic puzzles, they're invitations to rethink the boundaries of physics itself. Whether they're tied to space-time's hidden fractures, the last gasps of ancient black holes, or something we haven't even dreamed up yet, one thing's certain: the universe is far weirder and far more wonderful than we ever suspected. And with every burst, it's handing us a chance to catch up. Among the most tantalizing and controversial explanations for fast radio bursts is the idea that we might not be listening to cosmic phenomena at all, but to something far more extraordinary, the signatures of an advanced extraterrestrial civilization. It's a theory that straddles the line between science and science fiction, fueled by the eerie precision of some repeating bursts. Take FRB 1211-2, for instance, with its irregular but persistent cadence, or the bizarre frequency sweeps of FRB 190120, which some have likened to a cosmic dial being tuned. Could these be intentional signals broadcast across the void, or perhaps something even more mind-bending, artifacts of alien technology, like interstellar light sails propelled by focused energy beams, leaving fleeting radio flashes in their wake? The idea isn't entirely without precedent. In the 1960s, physicist Freeman Dyson speculated about civilizations harnessing the energy of stars, while the Breakthrough Listen project actively scans the cosmos for artificial signals. Even the repetitive nature of some FRBs mirrors what human engineers might design, a beacon meant to conserve energy by pulsing rather than broadcasting continuously. And then there's the WOW signal of 1977, a mysterious radio blip that still haunts astronomers as a potential, though unconfirmed, hint of extraterrestrial contact. Fast radio bursts, with their galaxy-spanning power and millisecond brevity, fit eerily well into this speculative framework, yet scientists urge caution. The universe is under no obligation to conform to our imagination, and extraordinary claims demand extraordinary evidence. So far, every peculiar feature of FRBs, their dispersion, polarization, and even repetition, has found plausible explanations within known physics. Magnetars, neutron star collisions, and black hole antics can account for the burst's energy and structure without invoking intelligence. Even the most tantalizingly artificial patterns, like FRB 1810-156's rhythmic bursts, could simply be the result of natural astrophysical resonances, like a cosmic bell ringing in the magnetic storm of a dying star. What's fascinating, though, is how the alien hypothesis forces us to confront our assumptions. If an advanced civilization were broadcasting FRBs, how would we distinguish their handiwork from nature's chaos? The answer lies in the details. Artificial signals might exhibit unnatural regularity, encode mathematical sequences, or transmit across narrow frequency bands, clues we've yet to spot in FRB data. Until then, the theory remains a captivating thought experiment, a reminder of how little we know about the universe's potential for life, and that's the real allure. Whether FRBs are the products of collapsing stars or alien megastructures, they've already achieved something remarkable. They've rekindled humanity's sense of wonder. Every time a new burst crackles across a telescope's sensors, it carries with it the faintest whisper of possibility that out there, in the silence between the stars, we might not be alone. And that's a mystery worth listening for. Plasma, the fourth state of matter, is far from just an exotic laboratory curiosity. In the vast expanses between galaxies, it's the invisible ocean through which fast radio bursts must travel, and its fingerprints are all over the signals we detect. Picture an FRB racing through space at light speed, its waves slicing through clouds of ionized gas so thin they'd qualify as a vacuum on Earth. Yet over billions of light years, even these wispy plasmas leave a mark, slowing lower frequency radio waves just slightly more than their higher frequency counterparts. The result, that telltale sweep astronomers call dispersion, a cosmic signature that lets them calculate a burst's journey with astonishing precision. But dispersion is more than just a measuring tape. The way an FRB's signal spreads reveals the hidden architecture of the universe. Denser patches of plasma, like the halos surrounding galaxies or the turbulent wakes of supernova remnants, impart subtle kinks in the dispersion curve, hinting at structures telescopes can't directly see. It's as if each burst carries a snapshot of every cosmic neighborhood it's passed through, exposing the universe's skeleton of ionized gas. Some FRBs even exhibit scattering, where their signals smear like sunlight through frosted glass, suggesting encounters with especially turbulent plasma near their birthplaces. Now consider the environment where these bursts originate. Magnetars, neutron stars, and black holes all dwell in plasmas so extreme they defy earthly physics. Near a magnetar's surface, magnetic fields trap plasma in seething vortices, while shocks from colliding neutron stars can heat gas to billions of degrees. These conditions don't just host FRBs, they sculpt them. Plasma acts like a cosmic lens, twisting the polarization of radio waves into intricate patterns that betray the strength and geometry of magnetic fields at the source. When astronomers detected FRB 190120's bizarre, corkscrew-like polarization, it pointed squarely to a magnetar wreathed in hypermagnetized plasma, its fields powerful enough to shred atoms into streams of charged particles. Yet plasma's role grows even stranger with repeating bursts. Some, like FRB 1211-2, show wild variations in dispersion between pulses, as if something is churning the plasma around the source between eruptions. One theory suggests asteroid-sized chunks of debris, vaporized into plasma as they plunge onto a magnetar, could create these shifting screens. Others propose plasma-filled winds from a companion star, or the turbulent aftermath of a supernova might be the culprits. What's clear is that plasma isn't just background noise. It's an active player in the FRB drama, shaping signals from their birth to their detection. By reading its subtle imprints, astronomers are turning these bursts into tools, probing the universe's missing matter, testing fundamental physics, and even hunting for the elusive filaments of the cosmic web. Every dispersed, scattered, or polarized burst is a message not just about its source, but about everything it's passed through on its way to us. And that makes plasma far more than a bystander. It's the universe's silent storyteller. Fast radio bursts aren't just cosmic mysteries, they're revolutionary tools, slicing through the darkness to reveal the universe's hidden scaffolding. For decades, astronomers have grappled with a troubling gap in their calculations. About half the ordinary matter predicted by the Big Bang seemed to be missing. Not dark matter, the truly elusive stuff, but baryonic matter, the protons and neutrons that make up stars, planets, and us. This missing matter wasn't truly gone. It was simply hiding, scattered as diffuse plasma in the voids between galaxies, too faint to see with telescopes. Enter FRBs. Every time one of these bursts streaks across the cosmos, its radio waves interact with this invisible plasma, slowing slightly in a process that leaves a distinct fingerprint called dispersion. The more plasma the signal traverses, the more its frequencies spread out like light passing through a prism made of ionized gas. This dispersion measure has become astronomy's newest yardstick. By analyzing hundreds of bursts from different distances, scientists have pieced together a three-dimensional map of the universe's missing matter, tracing the faint tendrils of plasma that weave galaxies together into the cosmic web. Some FRBs, like the distant FRB 180908, have dispersion measures so high they've revealed plasma reservoirs in places once thought empty, vast halos around galaxy clusters where gas lingers at temperatures too hot to emit light. Others, like FRB 190523, show unexpected spikes in their dispersion, hinting at previously undetected filaments of matter stretching between galactic superclusters. But the real magic lies in the details. Unlike traditional methods that rely on painstakingly measuring the faint glow of intergalactic gas, FRBs deliver their measurements in milliseconds with precision that's rewriting textbooks. When the repeating burst FRB 1211-2 flared up again in 2021, astronomers noticed its dispersion had increased slightly since its last outburst, evidence that the plasma around its host galaxy had grown denser, perhaps stirred by a recent supernova or the awakening of a central black hole. These dynamic readings offer something static observations never could: a real-time window into how cosmic ecosystems evolve. The implications stretch beyond mere mapping. FRB dispersion has become a laboratory for fundamental physics, testing whether light travels at the same speed across all frequencies, a cornerstone of Einstein's relativity. So far, the universe gets a passing grade, but with enough bursts, even minuscule deviations could hint at new physics. There's also the tantalizing prospect of weighing the entire cosmic web. By comparing FRB dispersion to the distribution of visible galaxies, astronomers have confirmed that the universe's missing baryons aren't missing at all, they're just hiding in plain sight, threaded through space in a gauzy network of ionized gas. What's astonishing is how these bursts, once dismissed as celestial oddities, have become indispensable. They're cosmic surveyors probing regions too distant or dim for traditional telescopes, and particle physicists testing the fabric of space-time itself. And with next-generation radio arrays coming online like the Square Kilometre Array, capable of detecting thousands more bursts, their potential is just beginning to unfold. Every new FRB isn't just a mystery to solve. It's a key turning in the lock of the universe's deepest secrets. Before CHIME, hunting fast radio bursts was like searching for lightning strikes with a magnifying glass, painstaking, slow, and reliant on sheer luck. Then came the Canadian Hydrogen Intensity Mapping Experiment, a radical telescope unlike any other. Imagine 4 massive half-cylinders stretching the length of a football field, their surfaces studded with over 1,000 antennas constantly bathing in radio waves from half the sky. This isn't just a telescope, it's a cosmic fire hose swallowing the entire northern sky every single day. Where traditional radio dishes focus on pinpricks of space, CHIME drinks in the whole horizon, catching bursts that would have slipped through the cracks of older technology. The results have been nothing short of revolutionary. In just its first year of operation, CHIME detected more FRBs than all previous telescopes combined, over 500 and counting. But it's not just the numbers that astonish, it's the diversity. CHIME has catalogued bursts that defy categorization, some repeating with military precision, others flickering just once and vanishing. There's FRB 1809016, a repeater with bursts so regular they could set your watch, and FRB 190720, whose single brilliant flash carried the energy of 100 million suns. Each detection chips away at old assumptions, revealing a cosmos far richer in radio fireworks than anyone dreamed. What sets CHIME apart isn't just its hunger for data, but its genius for pattern recognition. Custom-built algorithms sift through terabytes of daily noise, flagging potential bursts in real time. This automated vigilance has uncovered subtle quirks like how some repeaters seem to remember their burst intervals, picking up right where they left off after months of silence. Others, like FRB 181214, arrive in clusters so tight they resemble cosmic machine gun fire. CHIME flood of data has even resurrected old mysteries. A handful of bursts appear to arrive in pairs or triplets, separated by milliseconds, hinting at sources that might hiccup multiple times in quick succession. Yet CHIME's greatest gift might be its ability to localize bursts with shocking precision. By leveraging the slight timing differences in how signals hit its 4 cylinders, it can often pinpoint FRBs to specific galaxies, something that once required painstaking follow-up with other telescopes. This leap has revealed host galaxies spanning the cosmic spectrum, dwarf galaxies barely holding themselves together, massive ellipticals devoid of young stars, and everything in between. The message is clear: FRBs don't discriminate. They emerge from cosmic backwaters and bustling galactic hubs alike, suggesting their origins might be as varied as the neighborhoods they call home. The telescope's impact extends beyond discovery. CHIME's sheer volume of detections has let astronomers perform statistical feats once thought impossible. By comparing burst rates across different distances, they've confirmed FRBs occur uniformly throughout the universe. No cosmic epoch holds a monopoly. Even more intriguing are the outliers, bursts with bizarre frequency structures or polarization twists that refuse to fit neat categories. These oddballs might represent entirely new classes of FRBs, or perhaps the same phenomena viewed from angles we've never seen before. As CHIME enters its 5th year, the question isn't just what it will find next, it's how these discoveries will reshape our understanding of the universe's most energetic enigmas. With upgrades rolling out to boost its sensitivity and sister instruments like CHORD expanding its reach, the telescope is poised to uncover bursts fainter, farther, and stranger than ever before. Every new detection is a reminder: we're not just mapping the universe's radio whispers anymore. We're starting to hear its voice. Pinpointing the exact origins of fast radio bursts is like trying to find a single blinking firefly in a pitch-black forest, except that firefly might be billions of light years away. This is where localization comes in, the painstaking process of tracing these fleeting signals back to their home galaxies. The challenge: most radio telescopes have fields of view so narrow they'd need pure luck to catch a burst in the act. That's where arrays like the Very Large Array in New Mexico change the game. With 27 dish antennas working in concert, the VLA acts like a cosmic net, catching bursts with a precision that can narrow their origins down to a tiny patch of sky, sometimes just a fraction of an arcsecond across. But why does this matter? Because knowing where a burst comes from transforms it from a curiosity into a Rosetta Stone. Take FRB 190120, localized by the VLA to a spiral galaxy 4 billion light-years away. Unlike earlier bursts tied to chaotic star-forming regions, this one emerged from a quieter galactic suburb, forcing astronomers to reconsider their magnetar theories. Then there's FRB 1810156, traced to a dwarf galaxy with frenetic star birth, a clue that young, massive stars might be key players in some burst. Every localization rewrites the rulebook, revealing environments as diverse as the bursts themselves. The real breakthrough comes when optical telescopes join the hunt. Once radio arrays like the VLA or ASCAP in Australia flag a burst's rough coordinates, observatories like Hubble or the Keck telescopes zoom in, searching for the faint glow of a host galaxy. This cross-revolution has uncovered startling patterns. Some bursts, like FRB 190523, originate near galactic centers where supermassive black holes lurk, while others, like FRB 180908, erupt from the outskirts, far from any obvious cosmic drama. These locations aren't just addresses, they're clues. A burst near a black hole might hint at tidal disruptions or jet interactions, while one in a star-forming region could point to magnetars born in supernova explosions. Yet localization does more than just map bursts, it measures the universe. By tying FRBs to specific galaxies with known distances, astronomers can cross-check cosmic expansion rates, testing whether our measurements of the universe's growth hold up across billions of light years. Even failed localizations teach us something. When the bizarrely active FRB 1211-2 was traced to a tiny, unassuming dwarf galaxy, it proved that colossal bursts don't require colossal hosts, appending assumptions about the environments capable of producing them. The next frontier, real-time alerts. Projects like the Deep Synoptic Array in California are refining localization to seconds, allowing telescopes worldwide to swivel toward bursts fast enough to catch potential afterglows in X-rays or visible light. Imagine capturing the flash of a neutron star collision moments after the radio burst arrives, or spotting an unexpected counterpart that cracks the mystery wide open. With each precise localization, we're not just finding where these bursts come from. We're piecing together how the universe's most extreme physics operates in wildly different corners of the cosmos. And that's how a millisecond flicker becomes a window into everything. Among the hundreds of fast radio bursts detected, one stands out for its eerie cosmic punctuality, FRB 180916. Unlike its erratic repeating cousins, this burst operates with metronomic precision, flaring up like clockwork every 16.35 days. It's as if the universe set an alarm, ringing with bursts that last just milliseconds but arrive on a schedule so reliable you could set your calendar by it. This isn't just unusual, it's a potential Rosetta Stone for decoding the origins of repeating FRBs. The 16-day cycle is a glaring clue. In astronomy, periodicity often means motion. Something is orbiting something else. Picture a magnetar, one of those ultramagnetic neutron stars, locked in a gravitational dance with a massive companion star. As the magnetar swings around its partner, its emissions might periodically align with Earth, creating bursts we detect only during specific phases of its orbit. Alternatively, the companion itself could be feeding material onto the magnetar, with the infalling gas triggering bursts at regular intervals like cosmic clockwork. Then there's the wildcard scenario, a black hole binary. Imagine two black holes circling each other, their immense gravity warping the space around them. If one harbors a swirling disk of superheated material, tidal forces could strip matter away at predictable intervals, sparking bursts each time the stolen plasma slams into the black hole's jet. The 16-day gap, that's simply the time it takes for the duo to complete their orbital waltz. What makes FRB 180916 so tantalizing isn't just its regularity, it's the implications. If this periodicity confirms an orbital origin, it would mark the first time we've directly tied an FRB to a specific celestial choreography. Already, the burst's host galaxy adds another layer of intrigue, a relatively quiet spiral, not the star-forming frenzy often associated with magnetars. This suggests the engines powering periodic FRBs might thrive in calmer cosmic neighborhoods, far from the chaos of stellar nurseries, yet mysteries linger. Why do some orbital phases produce multiple bursts while others go silent? Could there be multiple mechanisms at play, with some bursts triggered by the companion's wind and others by the neutron star's own quakes? And most perplexing of all, why 16 days? That's unusually long for a compact binary system, hinting at either an unusually wide separation between the objects or an entirely new class of FRB progenitor we've yet to imagine. Every burst from FRB 180916 is a fresh opportunity to test these theories. Astronomers now watch its host galaxy like clockwork, anticipating each expected eruption with arrays of telescopes poised to capture every nuance, changes in polarization, subtle frequency shifts, or even a flicker of associated light. With each cycle, we're not just observing a cosmic curiosity, We're witnessing a celestial timepiece, ticking away the seconds until we finally unravel what makes it chime. Fast radio bursts don't just push the limits of what we know, they shatter them. Take the most energetic bursts on record, like FRB 190523, which in just milliseconds unleashed the equivalent of 500 million suns worth of energy. To put that into perspective, that's more power than our entire galaxy emits in the same fleeting instant. And yet, the leading suspects behind these bursts, neutron stars, magnetars, are barely the size of a city. How can something so compact produce explosions that dwarf the output of quasars, some of the most luminous objects in the universe? This is the energy problem, and it's forcing physicists to rewrite the rules of cosmic power generation. At first glance, the numbers don't add up. Neutron stars, while incredibly dense, shouldn't be able to convert more than a fraction of their stored energy into a coherent radio blast without violating known physics. Traditional models of magnetic reconnection, the process where twisted magnetic field lines snap and release energy, fall short by orders of magnitude. Even the most violent starquakes on magnetars, those cosmic powerhouses with magnetic fields 1,000 trillion times stronger than Earth's, struggle to account for the sheer intensity of the brightest FRBs. It's like trying to power a nuclear reactor with an AA battery. The scales just don't match. One radical solution gaining traction involves relativistic shocks. Picture a magnetar's magnetic field acting like a cosmic slingshot, accelerating particles to near light speed. If these particles collide with surrounding plasma or debris, the resulting shockwaves could focus energy into a narrow, coherent beam, essentially a cosmic laser operating at radio frequencies. This synchrotron maser mechanism, while still theoretical, could amplify a neutron star's output to FRB levels by harnessing the chaotic interplay of magnetic fields and ultra-relativistic particles. Some simulations even suggest that under the right conditions, these shocks could channel up to half the system's energy into a single, directed burst, solving the efficiency puzzle at a stroke. Yet not every burst fits this mold. Some FRBs exhibit energy distributions so extreme they hint at entirely different engines. One provocative idea involves superconducting cosmic strings, hypothetical relics from the early universe vibrating like plucked guitar strings and releasing stored energy as FRB scale flashes. Another theory points to black hole light sails, where collapsing neutron stars or evaporating primordial black holes convert their entire mass into a focused energy pulse. These scenarios flirt with the edge of known physics, suggesting that FRBs might be our first glimpse of phenomena beyond standard astrophysical models. The stakes couldn't be higher. If neutron stars really can produce FRB-level energy through some undiscovered process, it implies there's a gap in our understanding of how matter behaves under the most extreme conditions. Magnetar magnetospheres, for instance, might host plasma instabilities or quantum effects that operate like cosmic transformers, stepping up energy to unprecedented levels. Or perhaps FRBs arise from the collective action of multiple neutron stars in tight clusters, their combined emissions masquerading as a single, impossibly bright burst. What's clear is that every new detection adds another piece to the puzzle. When telescopes caught FRB 201,906 flashing from a galaxy 6 billion light-years away, its energy profile defied even the most optimistic shock models, reigniting debates about exotic physics. Meanwhile, the repeating burst FRB 1211-2 occasionally fires off weaker mini-bursts alongside its titanic flares, suggesting the same source can operate across a startling range of energies. These variations might hold the key different mechanisms kicking in under different conditions, like gears shifting in a cosmic transmission. The energy problem isn't just academic. Crack it, and we might unlock new ways to understand everything from gamma-ray bursts to the birth cries of black holes. Until then, every millisecond burst is a reminder. The universe has power sources we've yet to imagine, and they're broadcasting their secrets in flashes almost too quick to see. Dark matter, the universe's most elusive ghost, makes up over 80% of all matter, yet it refuses to interact with light, leaving us only its gravitational fingerprints. Now imagine if this invisible enigma held the key to unlocking another cosmic puzzle: fast radio bursts. It's a theory as tantalizing as it is speculative, weaving together two of astronomy's greatest mysteries. Could dark matter, in some hidden way, be triggering these brilliant flashes across the cosmos? One provocative idea suggests that dark matter particles, under the right conditions, might annihilate or decay, releasing bursts of energy detectable as FRBs. Picture a dense clump of dark matter, perhaps a primordial black hole or an exotic particle cluster, collapsing or vibrating in the depths of space. As it destabilizes, the energy released could ignite a shock wave in surrounding plasma, producing the telltale radio burst we observe. The appeal of this theory lies in its elegance. It ties the unexplained power of FRBs to the universe's most abundant yet invisible substance, but the evidence so far is thin. No FRB has yet been definitively linked to regions of high dark matter density, like the halos surrounding galaxies. And while some bursts originate from areas where dark matter is thought to concentrate, they also align with more conventional suspects: magnetars, neutron stars, and black holes. Still, the possibility lingers, fueled by the sheer strangeness of both phenomena. Could certain types of dark matter actions or other hypothetical particles interact weakly with magnetic fields, creating conditions ripe for FRB production? The challenge is testing these ideas. Unlike magnetars or colliding stars, dark matter leaves no electromagnetic trail to follow. If an FRB were truly born from dark matter, its signal might carry subtle anomalies, perhaps an unusual polarization pattern or an absence of associated visible light from a host galaxy. Some theorists even propose that certain repeating FRBs could be echoes of dark matter structures oscillating in distant space, their periodic bursts reflecting the rhythm of an invisible cosmic pendulum. Yet for all its intrigue, the dark matter connection remains a long shot. Most astronomers lean toward astrophysical explanations firmly rooted in known physics. But that's the beauty of FRBs. They're so bizarre, so defiant of easy categorization, that they leave room for the extraordinary. Whether dark matter plays a role or not, the mere act of questioning it stretches our understanding of what's possible. And in that space between the known and the unknown, between the seen and the unseen, lies the thrilling frontier of discovery. Every new burst is a chance to ask, are we hearing the whispers of dark matter itself, or is the universe playing a deeper game we've yet to comprehend? The hunt for fast radio bursts is entering a golden age, with next-generation telescopes poised to transform these cosmic whispers into a deafening chorus. At the forefront stands the Square Kilometre Array, or SCAR, a revolutionary observatory now rising across 2 continents. Imagine a forest of radio antennas spanning Australia and South Africa, their combined power creating a dish with a collecting area of, you guessed it, 1 square kilometre. This behemoth won't just detect FRBs, it will drown in them, capturing potentially thousands every year with a sensitivity that could spot a cell phone signal from another galaxy. But SKA isn't just about quantity. Its exquisite resolution will pinpoint burst locations to individual stars within distant galaxies, letting astronomers cross-reference them with supernova remnants, magnetar neighborhoods, or black hole jets like never before. Meanwhile, machine learning algorithms are turning the flood of data into actionable discoveries. Traditional methods would drown in the millions of cosmic false alarms, pulsars, satellite glitches, even microwave ovens, masquerading as FRBs. Now, neural networks trained on past bursts sift through this noise in real time, flagging genuine signals within seconds. Some systems, like the one used by Canada's CHIME telescope, have learned to recognize subtle sub-pulse structures that hint at a burst's origin before human eyes ever see the data. Others correlate FRBs with gravitational wave detections or neutrino alerts, hunting for multi-messenger events that might reveal their engines, the real game changer. Speed. Projects like the Deep Synoptic Array in California can now localize bursts within arcseconds fast enough to alert optical telescopes while the afterglow still lingers. Picture this: an FRB flares up, and within minutes, instruments from radio dishes to X-ray satellites swing into alignment, capturing every wavelength from the same cosmic cataclysm. Such coordinated observations might finally catch a magnetar mid-quake or a neutron star collision in the act, linking bursts to their progenitors beyond doubt. But the surprises won't stop there. With SKA's ears tuned to lower frequencies than ever, we might discover entirely new classes of FRBs, ones too faint or too spread out for current telescopes. Some theorists predict bursts lasting microseconds, or ones stretched by cosmic expansion into eerie, slow-motion signals. Others speculate about orphaned FRB bursts whose visible light was absorbed by interstellar dust, leaving only radio echoes to reach us. Then there's the tantalizing prospect of detecting a burst from the universe's infancy, a relic from when the first stars and black holes were taking shape. What makes this moment so electrifying isn't just the technology, it's the questions we're finally equipped to answer. Are all repeating FRBs magnetars, or do some stem from stranger beasts? Do one-offs and repeaters represent a continuum or entirely distinct phenomena? And could some bursts encode information about quantum gravity or dark matter in their polarized signals? The next decade promises more than just data. It offers the chance to rewrite astrophysics textbooks. Every millisecond burst captured by SKA's vast net will be a potential Rosetta Stone, waiting to reveal how the universe's most extreme environments bend matter, energy, and space-time itself to their will. As these telescopes come online, one thing is certain: the era of FRBs as mere curiosities is ending. They're becoming precision tools, cosmic beacons lighting up the universe's hidden corners. And with each new detection, we're not just solving a mystery, we're learning how to listen to the cosmos in a whole new way. Fast radio bursts have transcended the realm of astrophysics to become cultural icons, sparking imaginations far beyond the scientific community. These millisecond flashes from the depths of space have found their way into blockbuster films, best-selling novels, and viral conspiracy theories, often portrayed as everything from alien distress signals to harbingers of cosmic doom. Take the Netflix series Another Life, where an FRB serves as the first breadcrumb in an interstellar treasure hunt, or Peter Watt's sci-fi novel, The Freeze Frame Revolution, which reimagines bursts as encrypted messages from ancient civilizations. Even video games like No Man's Sky weave FRBs into their lore as mysterious waypoints guiding players across virtual galaxies. This cultural fascination isn't accidental. It taps into humanity's oldest questions about whether we're alone in the universe and what might be signaling us from the void. What makes FRB such potent storytelling fuel is their perfect blend of scientific credibility and unanswered questions. Unlike purely fictional phenomena like wormholes or warp drives, these bursts are undeniably real, verified by telescopes and published in peer-reviewed journals. Yet their origins remain uncertain enough to leave room for wild speculation. This delicate balance between fact and mystery mirrors classic sci-fi tropes like Arthur C. Clarke's monolith from 2001, A Space Odyssey, where advanced science becomes indistinguishable from magic, when scientists themselves openly debate whether some bursts could, however unlikely, be technosignatures. It gives storytellers just enough plausibility to run with the idea. Cultural impact goes beyond fiction. FRBs have become modern-day equivalents of the WOW, Signal, or Mars Canal's blank canvases for humanity's hopes and fears about extraterrestrial life. Online forums buzz with theories tying bursts to ancient alien prophecies or secret government projects. Some artists have even translated FRB data into musical compositions, turning the dispersion sweeps of real detections into haunting electronic melodies. This interdisciplinary appeal reveals something profound. In an age of information overload, these cosmic enigmas remind us that the universe still holds genuine mysteries no algorithm can fully explain. Yet there's a fascinating tension between scientific caution and creative license. While astronomers painstakingly avoid the word aliens in their papers, Hollywood happily runs with it, often exaggerating the signal's properties for dramatic effect. The bursts that take years to localize in reality become instant GPS coordinates in movies. The milliseconds-long flashes stretch into sustained transmissions. This gap between fact and fiction isn't harmful, it's generative, sparking public interest that often leads to increased funding for radio astronomy. Some researchers even credit sci-fi depictions with helping recruit the next generation of astrophysicists, much as Star Trek inspired real-world engineers. Perhaps the most enduring cultural legacy of FRBs lies in how they've reshaped our cosmic perspective. Like pulsars before them, once jokingly dubbed LGM for little green men, these bursts have evolved from scientific oddities to cultural touchstones. They've given us a new vocabulary for wondering about the unknown, a reminder that the universe is stranger than we imagine. And in that space between detection and understanding, between the published paper and the Netflix script, lies something rare, a genuine mystery that belongs as much to poets as to physicists, inviting us all to look up and wonder what might be calling from the dark. Not every blip or burst from the cosmos is a fast radio burst. In fact, most aren't. The universe is a noisy place, crackling with natural and man-made signals that can masquerade as FRBs. Pulsars, for instance, are cosmic lighthouses that emit regular radio pulses, but their steady rhythms and predictable periods make them easy to distinguish from FRB's erratic, one-off flashes. Then there's radar echoes bouncing off satellites or space debris, creating false alarms that trick even seasoned observers. And let's not forget Earth's own interference. Microwave ovens, cell towers, and even faulty observatory equipment have all been caught impersonating distant cosmic explosions. So how do astronomers separate the celestial wheat from the chaff? It starts with the burst dispersion measure, the fingerprint left by intergalactic plasma. True FRBs show a characteristic sweep across frequencies, with lower radio waves arriving slightly later than higher ones, a telltale sign they've traversed vast cosmic distances. Terrestrial interference, by contrast, lacks this dispersion, appearing equally crisp across all frequencies, but nature loves to complicate things. Some pulsars in binary systems exhibit dispersion similar to FRBs, and rare atmospheric phenomena like peritons, radio bursts caused by microwave ovens opening mid-cycle, once fooled researchers into thinking they discovered a new class of cosmic signal. The real detective work begins with polarization. Many FRBs carry a distinct twist in their radio waves, a signature of extreme magnetic fields at their source. Instruments like the Green Bank telescope can analyze this polarization, weeding out imposters like solar flares or auroras, which exhibit different magnetic signatures. Then there's the localization game. True FRBs pinpointed to distant galaxies via optical follow-ups are virtually impossible to confuse with local noise. The infamous Lorimer burst was initially met with skepticism precisely because it couldn't be replicated until independent telescopes confirmed similar signals from deep space. Yet the most insidious mimics are the ones that play by FRB rules. Take active galactic nuclei, supermassive black holes whose jets occasionally spit out millisecond radio flares. These can masquerade as FRBs until astronomers spot their lingering X-ray emissions or trace them back to galaxies already known for violent activity. Even neutron star collisions, while legitimate cosmic events, sometimes emit radio bursts that blur the line between FRBs and other transient phenomena. What's fascinating is how the hunt for FRBs has sharpened astronomy's tools overall. Machine learning algorithms trained on mountains of telescope data now flag anomalies in real time, while citizen science projects like SETI at home sift through radio static for hidden gems. The lesson: in a universe brimming with wonders, the rarest discoveries often lie buried in the noise, waiting for patient, meticulous science to tease them out. Every burst that survives this gauntlet of scrutiny isn't just a curiosity. It's a testament to the rigor that turns speculation into revelation. Fast radio bursts are the ultimate cosmic speedsters racing across the universe at light speed, covering distances so vast that by the time they reach us, their sources may have vanished into stellar history. Imagine a signal so fast it could circle Earth 7 times in a single second, yet so fleeting that its entire existence fits into the blink of an eye. That's the paradox of FRBs. They traverse billions of light years, enduring eons of travel, only to flash through our telescopes in milliseconds. But within that vanishingly brief window, they pack a staggering amount of information, like a cosmic telegram compressed into a nanosecond. What makes their speed so mesmerizing isn't just the raw physics, it's how that velocity shapes their detectability. Because these bursts outpace anything but light itself, they arrive at Earth almost entirely unchanged from their original state, untouched by the interstellar and intergalactic obstacles that distort slower-moving signals. Their high-frequency radio waves slice through cosmic dust clouds, plasma fields, and even the turbulent magnetic halos of galaxies, delivering remarkably clean data despite their epic journeys. This purity is what lets astronomers decode the burst's dispersion measures with such precision, turning each one into a cosmic yardstick for measuring the universe's hidden matter. Yet their brevity is equally critical. If FRBs lingered even a fraction of a second longer, their signals would smear across time, blurring the fine details that reveal their origins. It's this razor-sharp timescale that allows us to catch the subtle fingerprints of their environments, the way certain frequencies scatter slightly more than others, or how the polarization twists in ways that betray the presence of intense magnetic fields. Some bursts, like FRB 190120, exhibit microsecond substructure within their millisecond envelopes, hinting at incredibly fine-tuned processes at their sources, perhaps magnetic reconnection events or shockwaves propagating through neutron star magnetospheres. The interplay between speed and transience also fuels their mystery. Because FRBs are so fleeting, they demand observatories with split-second reflexes. Telescopes like CHIME and ASCAP don't just scan the skies, they act as high-speed cameras, capturing snapshots of the radio universe thousands of times per second. Without this technological ballet, most bursts would slip through unnoticed, their existence lost to the cosmic background hum. It's as if the universe is whispering its secrets in a language of hyper-compressed pulses, and we've only just learned to listen at the right tempo. But perhaps the most astonishing thing about FRBs speed isn't their velocity, it's how they warp our perception of time. A burst detected today might have begun its journey when Earth was still a molten rock, or before the Milky Way took its current shape. In that sense, these signals are more than just messages from distant space. They're time capsules carrying echoes of epochs long past. And when we catch them, if only for a millisecond, we're not just observing the universe, we're touching a moment frozen in light, a spark from a distant shore that flickers into view just long enough to remind us how much lies beyond our grasp. What if fast radio bursts aren't just cosmic anomalies, but messages from other universes? It's a theory that dances on the edge of science fiction, yet some physicists dare to entertain the idea. In the wildest corners of multiverse cosmology, FRBs have been proposed as echoes of bubble universes colliding with our own, or as gravitational tremors leaking through hidden dimensions. Picture this: a parallel reality with slightly different physical laws experiences a cataclysm, a black hole merger, a quantum phase transition, and the shockwaves ripple through the fabric of spacetime itself, manifesting in our universe as a fleeting radio burst. The math, while speculative, is eerily elegant. Certain string theory models predict that such cross-dimensional leakage could produce electromagnetic signatures startlingly similar to the dispersion patterns we observe in FRBs. Of course, this isn't mainstream science yet. The multiverse hypothesis remains one of cosmology's most contentious ideas, lacking direct evidence, but consider the peculiarities that fuel the speculation. Some bursts exhibit polarization twists that defy conventional magnetic field explanations, as if their radio waves have been scrambled by passage through an exotic medium. Others, like FRB 190120, arrive with frequency structures that resemble theoretical predictions of brain-world collisions, hypothetical events where membrane-like universes brush against one another in higher dimensional space. Even the sheer isotropy of FRB distribution, their equal scattering across the sky, mirrors what you'd expect if their origins weren't tied to galaxies at all, but to something beyond our cosmic horizon. Skeptics rightly point out the razor-thin line between creative theorizing and wishful thinking. After all, FRBs fit comfortably within known astrophysics. Invoking parallel universes might seem like using a quantum sledgehammer to crack a neutron star nut. Yet history shows that today's fringe ideas sometimes become tomorrow's textbooks. The cosmic microwave background radiation was once dismissed as mere telescope static before revolutionizing our understanding of the Big Bang. Could FRBs play a similar role for multiverse theory? The key lies in testable predictions. If bursts from certain sky regions exhibit anomalous energy distributions or polarization angles that resist conventional explanations, they just might hint at physics beyond our universe's walls. What makes this speculation so electrifying isn't just its audacity, but its humility. The multiverse angle forces us to confront how little we truly know about reality's boundaries. Whether FRBs are cosmic lighthouses, magnetar tantrums, or something far stranger, their very existence whispers a tantalizing truth. The universe or universes are far richer, far weirder than we've dared to dream. And that's a mystery worth chasing, no matter where it leads. The possibility that fast radio bursts could be more than natural phenomena, that they might carry the fingerprints of intelligence, forces us to confront one of science's oldest ethical dilemmas. What happens if we're not alone and the universe is trying to get our attention? This isn't just speculative fiction. It's a serious debate echoing the protocols of SETI, the search for extraterrestrial intelligence, where researchers have long grappled with how and whether to respond to cosmic signals. The difference here is urgency. While traditional SETI assumes deliberate, sustained contact, FRBs are fleeting, leaving no time for committees or careful deliberation. If one of these bursts were ever deemed artificial, humanity would face an immediate choice: answer back or observe in silence. The arguments for caution are compelling. History is littered with first contact scenarios gone awry, from colonial encounters to invasive species introductions. Broadcasting our presence without understanding the sender's intentions could invite risks we can't foresee. Astrophysicists like Stephen Hawking famously warned against announcing ourselves to potentially hostile civilizations, comparing it to the Native Americans signaling Christopher Columbus, a decision with irreversible consequences. Some scientists advocate for a passive listening approach, treating FRBs as cosmic curiosities rather than invitations to dialogue. After all, replying to a burst from a galaxy billions of light years away would mean committing to a conversation spanning generations, with no guarantee the sender even exists by the time our response arrives. Yet the counterarguments simmer with curiosity. If FRBs were artificial, ignoring them might represent a failure of cosmic proportions, a missed chance to join a galactic community, or decode knowledge far beyond our own. The very act of replying, even symbolically, could inspire global cooperation, much like the golden record aboard Voyager did in the 1970s. And let's be honest, the allure of cracking an interstellar code, of proving we're not the universe's sole thinkers, is a siren call few civilizations could resist. Striking a balance is the real challenge. Organizations like the International Academy of Astronautics have proposed frameworks for responding to extraterrestrial signals, emphasizing international consensus and multidisciplinary review. But FRBs add a twist. Their unpredictability means any protocol must be pre-established, not debated in the heat of discovery. Imagine a scenario where a burst structure contains mathematical sequences or prime numbers, hallmarks of artificiality. Would we have the discipline to analyze without transmitting, or would excitement override caution? Underlying this debate is a deeper question about humanity's role in the cosmos. Are we observers content to study the universe from a distance, or participants willing to engage with whatever or whoever might be out there? Fast radio bursts, whether natural or not, hold up a mirror to our own ambitions and fears. They force us to weigh the hunger for connection against the prudence of anonymity, to decide whether the universe is a place we merely inhabit or one we dare to converse with. And until we know more, that tension between silence and speech, between hiding and reaching out, might be the most human response of all. Fast radio bursts aren't just flashes in the cosmic dark. They're time travelers carrying echoes of the universe's expansion in their stretched and warped signals. As these bursts race across billions of light years, they don't just move through space, they surf the very fabric of spacetime itself, stretched by the universe's relentless expansion. This phenomenon, known as cosmological redshift, affects all light traveling vast distances, but with FRBs, it's coupled with something extraordinary. Their millisecond precision lets astronomers measure the stretching of spacetime itself with unprecedented accuracy. Each burst's dispersion, the way its lower frequencies lag behind its higher ones, acts like a cosmic speedometer, revealing how much the universe has expanded during the signal's journey. But the real magic lies in the details. Some FRBs exhibit subtle anomalies in their redshift patterns, tiny deviations from what Einstein's equations predict. These wrinkles could hint at dark energy's mysterious influence, the force accelerating the universe's expansion, or even uncover flaws in our understanding of gravity itself. Take FRB 180908, a burst from a galaxy so distant its light has traveled for nearly 6 billion years. Its signal arrived slightly more stretched than standard models predicted, as if the universe expanded faster in certain regions than we'd accounted for. Is this a measurement error, or could it point to something deeper, a cosmic unevenness in the fabric of space-time? Then there's time dilation's eerie side effects. For repeating bursts like FRB 1211-2, astronomers have noticed something peculiar. Later bursts from the same source appear to arrive slightly more stretched than earlier ones. At first glance, this seems impossible. How could the universe expand noticeably over just a few years? The answer lies in the burst's environment. If the source is orbiting a massive object like a black hole, Einstein's general relativity dictates that time would pass slower for the burst in the intense gravitational field, subtly altering its observed frequency when it finally reaches us. This gravitational redshift stacks atop cosmological redshift, creating a fingerprint of the extreme physics near the FRB's birthplace. What's astonishing is how these minute distortions turn FRBs into cosmic seismographs, sensitive to the slightest tremors in spacetime's architecture. By comparing bursts from different epochs, some emitted when the universe was half its current age, scientists can reconstruct the expansion history of the cosmos, testing whether dark energy's push has changed over billions of years. Already, early analyses suggest tantalizing inconsistencies with the standard cosmological model, hinting that dark energy might not be the constant force we've assumed. Could FRBs reveal that it's strengthening, weakening, or even fluctuating? The data isn't conclusive yet, but every new burst sharpens the picture. Beyond expansion, FRBs might expose spacetime's hidden wrinkles. Quantum gravity theories predict that on microscopic scales, spacetime isn't smooth but foamy, a seething froth of virtual particles and black holes. As FRBs traverse these unimaginably tiny fluctuations, their highest frequency waves could scatter slightly, leaving imprints in the burst's polarization. While no such signal has been definitively detected, next-generation telescopes like the Square Kilometre Array could finally have the sensitivity to spot these quantum fingerprints, offering a glimpse into physics at scales 1 trillion times smaller than an atom. The most profound revelation, though, might be how FRBs expose spacetime as an active participant in the universe's story, not just a static stage. Every burst that reaches us has been molded by the cosmos' growth, bent by gravity's grip, and potentially buffeted by quantum turbulence. They're not just messages from distant galaxies, they're mirrors reflecting the universe's evolving geometry. And with each detection, we're not just mapping where these bursts come from, we're measuring how the very space between us and them has stretched, twisted, and breathed across eons. In that sense, FRBs are more than yardsticks or time capsules. They're the universe's way of showing us its stretch marks, the scars of its ceaseless expansion, written in light. Among the 30 unexplained bursts lighting up our cosmic map, no two are exactly alike. Each pulses with its own rhythm, energy, and personality. Take FRB 1211-2, the repeater that fires off like a cosmic metronome, its sporadic outbursts clustering in bursts of activity before falling silent for months. Contrast that with FRB 190523, a one-off titan whose single millisecond flash packed more energy than our sun emits in decades, then vanished without a trace. Then there's the enigma of FRB 1810-156, whose signal drifts downward in frequency like a sigh, as if the burst itself is sliding down a cosmic slide, a phenomenon astronomers call the sad trombone effect. These quirks aren't just curiosities, they're clues. The way FRB 190120's radio waves twist into corkscrew patterns points to a magnetar wrapped in a magnetic straitjacket. while FRB 201906's jagged substructure, tiny pulses nested within the main burst, hints at shockwaves ricocheting through a neutron star's turbulent surroundings. Even the quiet ones, like FRB 170720, which barely registers above the cosmic noise, might be the most revealing. Their faintness suggests they're either incredibly distant or born from a less violent process, filling in the gaps between the universe's radio screamers and whisperers. Cataloging these differences is like assembling a cosmic fingerprint database. Some bursts, like those from FRB 180916, arrive with near-perfect periodicity, their 16-day cycles implicating orbital dynamics, perhaps a neutron star dancing with a companion. Others, like FRB 2020114, defy patterns entirely, appearing once and never again, as if the universe pressed a cosmic mute button. Then there's the energy spectrum. FRB 190523's staggering output dwarfs the gentler repeater FRB 180301, suggesting some engines operate at full throttle while others idle. The real intrigue lies in the outliers. FRB 190720's signal is so clean, so devoid of scattering, it must have traveled through a near-perfect void, an intergalactic desert devoid of plasma. Meanwhile, FRB 20181214's radio waves are so twisted by magnetic fields, they imply a birthplace steeped in chaos, like the accretion disk of a supermassive black hole. These extremes aren't noise, they're signposts marking the boundaries of what's possible in the FRB zoo. What emerges isn't chaos but a hidden taxonomy. Repeaters cluster in certain host galaxies, often dwarf galaxies teeming with young stars, while one-offs favor more sedate environments. High-energy bursts tend to show more polarization, their radio waves aligned as if squeezed through a cosmic filter, while the faint ones often arrive unpolarized, like static from a broken radio. This divergence suggests multiple recipes for FRBs: magnetar quakes, neutron star collisions, black hole jets, each leaving a distinct signature in the burst's DNA. Yet for all their differences, these 30 bursts share one haunting trait: they refuse to fit neatly into boxes. Even within categories, surprises lurk. Some repeaters, like FRB 180916, adhere to strict schedules, while others, like FRB 1810156, erupt in fits and starts as if something asteroid impacts. Magnetic reconnection is jostling their engines unpredictably. The universe seems to be showing us a spectrum of violence, from controlled detonations to cosmic grenades, with no clear dividing line. This diversity might be the key to unlocking their origins. If all FRBs stemmed from a single phenomenon, their signals would wear similar masks. Instead, their variety screams multiplicity, a universe where neutron stars, black holes, and who knows what else all contribute to the chorus. The 30 bursts we're tracking aren't just a sample. They're a mosaic, each piece reflecting a different facet of the cosmos's most extreme physics. And as the catalog grows, so does the chance that patterns hidden in the noise will finally snap into focus. Every new burst added to this list isn't just another data point. It's a stroke on a canvas we're only beginning to see, a fragment of a larger picture that might one day reveal whether we're witnessing a single universal phenomenon, or 30 different ways the universe shouts into the dark. Deep inside a neutron star, matter isn't just dense, it's utterly alien. Protons and electrons crushed together form a bizarre quantum soup called neutron superfluidity, where particles flow without friction, as if the star's core has become a frictionless quantum river. This isn't just theoretical exoticism, it's the reality of matter compressed beyond earthly limits. And it's precisely this quantum strangeness that might hold the key to unlocking some of fast radio bursts' most perplexing features. Take the repeating bursts with their erratic yet sometimes rhythmic patterns. Traditional astrophysics struggles to explain why some FRBs flicker like a cosmic strobe light unless you invoke quantum turbulence. Picture a Magnetar's superfluid interior suddenly disturbed by a starquake, sending shockwaves rippling through this quantum fluid. The resulting vortices, whirlpools of spinning neutrons, could twist magnetic field lines like spaghetti, snapping them with enough force to launch an FRB. These quantum hiccups might even explain why some repeaters seem to remember their burst intervals, as if an underlying quantum oscillator is keeping time beneath the chaos. Then there's the polarization mystery. Some bursts arrive with radio waves twisted into intricate spirals, a phenomenon known as circular polarization. This doesn't just hint at strong magnetic fields, it suggests quantum-scale interactions, where the spin of particles in a superfluid aligns like microscopic compass needles, imprinting their signature on escaping radio waves. The extreme magnetic fields of magnetars, reaching up to a quadrillion times Earth's, could amplify these quantum effects to cosmic proportions, turning the star into a natural particle accelerator capable of generating FRBs. But the quantum rabbit hole goes deeper. Quantum entanglement, the eerie connection between particles across vast distances, might play a role in focusing FRB energy. If entangled particles near a magnetar's surface suddenly align, they could release coordinated bursts of radiation, channeling energy into a narrow beam instead of letting it dissipate uselessly into space. This could explain how FRBs achieve their staggering brightness without violating energy conservation. It's as if the universe has built-in quantum amplifiers lurking in the hearts of dead stars. The most speculative and thrilling idea involves quantum vacuum breakdown. Near a magnetar's surface, magnetic fields grow so intense they might rip spacetime itself apart, creating a froth of virtual particles that blink in and out of existence. If these particles collide in just the right way, they could release a cascade of energy detectable as an FRB. This would mean some bursts aren't just astrophysical events. They're glimpses of quantum field theory pushed to its breaking point, a regime where even the vacuum of space crackles with potential. Of course, quantum explanations come with caveats. Neutron star interiors are notoriously difficult to model, and quantum effects at such scales often defy intuition. Yet the tantalizing overlaps between FRB observations and quantum predictions are hard to ignore. When bursts exhibit fine-scale substructure, tiny pulses within pulses, it mirrors the discrete energy levels of quantum systems. When their polarization defies classical explanations, it whispers of spin states and superposition. This isn't just about solving the FRB puzzle. It's about using these cosmic flashes to test quantum mechanics in conditions no lab could ever replicate. Each burst becomes a natural experiment, probing whether quantum laws hold firm under gravity's most extreme dictatorship or if new physics emerges at the edge of collapse. The answers might rewrite textbooks, revealing how the universe stitches together the very large and the very small 1 millisecond burst at a time. The search for fast radio bursts isn't just the domain of professional astronomers. It's a cosmic treasure hunt where anyone with curiosity and an internet connection can join the chase. Projects like SETI at home pioneered this approach, harnessing idle computer cycles from millions of volunteers worldwide to sift through radio telescope data for alien signals. Now that same grassroots spirit is supercharging FRB research. Platforms like Zooniverse's Radio Galaxy Zoo and the Einstein at Home project invite everyday enthusiasts to scan data for the telltale dispersion sweeps of FRBs, turning coffee shop laptops into virtual radio telescopes. The impact is staggering. In one recent project, amateur volunteers helped classify over 20,000 potential FRB candidates in weeks, a task that would have taken a single researcher years. But you don't need a supercomputer to contribute. Amateur astronomers with backyard radio telescopes or even modified TV antennas have begun capturing FRB-like signals, sharing their findings through networks like the American Association of Variable Star Observers. While most lack the sensitivity to detect extragalactic bursts, they've proven invaluable for monitoring our own galaxy's magnetars, catching rare radio flares that mirror FRB physics on a smaller scale. Others contribute by analyzing publicly available data from CHIME or ASCAP, spotting anomalies that automated algorithms might miss. After all, the human brain excels at pattern recognition, sometimes noticing subtle quirks, like a burst's faint secondary pulse or an unusual polarization twist that machines dismiss as noise. The beauty of this collective effort lies in its diversity. A high school student in Norway once flagged a repeating burst that had slipped past professional filters simply because she noticed its dispersion curve looked off. A retired engineer in Australia, tinkering with radio hardware in his garage, helped refine calibration techniques now used by major observatories. Even smartphone apps like the FRB Project gamify the search, letting users swipe through frequency plots to identify potential signals while learning the science behind them. This isn't just about crowdsourcing labor, it's about democratizing discovery. When the next great burst lights up the sky, it could be a teacher in Tokyo or a farmer in Kenya who first spots it, their name etched alongside astrophysicists in the ensuing research paper. And as telescopes like the Square Kilometre Array come online, generating data floods no single team could hope to process alone, the role of citizen scientists will only grow. The universe doesn't care who's listening, only that someone is. And in that shared act of listening across continents and cultures, we're reminded that the greatest mysteries belong not just to scientists, but to anyone willing to look up and wonder. From magnetars to alien megastructures, these 30 unexplained radio bursts have rewritten the cosmic rulebook, proving the universe is far stranger than we ever imagined. Every flicker of energy racing across the void carries layers of unanswered questions, each one peeling back another mystery like the pages of an ancient celestial manuscript. Some bursts scream from the hearts of dying stars, their magnetic fields twisted into cosmic knots. Others whisper from the edges of black holes where gravity bends reality itself. And a few defy explanation entirely. Their patterns so peculiar they ignite debates stretching from university lecture halls to late-night online forums. The beauty of these enigmas isn't just in their complexity, it's in how they've united scientists worldwide in a shared quest for understanding. Astronomers once dismissed the first FRB as a telescope glitch, but today, observatories on every continent stand ready to pivot at a moment's notice, chasing bursts that vanish faster than a snap of the fingers. The hunt has spawned entirely new fields of study, from plasma cosmology to quantum gravity, all because of a signal shorter than a heartbeat. Yet for every mystery solved, the cosmos seems to conjure 10 more. Why do some bursts repeat while others vanish without a trace? Could their sheer variety hint at undiscovered celestial objects or even new laws of physics? The answers might lie in the next flash of data, the next burst caught mid-eruption by a vigilant telescope, and with instruments like the Square Kilometre Array coming online, capable of detecting thousands of FRBs a year, we're on the cusp of a revolution. What makes this pursuit so electrifying isn't just the science, it's the humility it demands. FRBs remind us that for all our knowledge, the universe still holds cards it hasn't shown us. They challenge us to stay nimble, to question assumptions, and to embrace the thrill of not knowing. Because somewhere out there, hidden in the static between the stars, the next great cosmic revelation might already be racing toward us, a flicker of radio waves carrying secrets we've only begun to dream of. So keep listening, keep wondering, and remember, the greatest discoveries often start with a single, fleeting signal. The next burst could change everything.